at the University of Tokyo. He got his PhD from the University of Tokyo under the supervision of Masahito Ueda, and was then postdoctoral fellow at the Max Planck Institute for Quantum Optics in Garching with the group of Ignacio Sirac. He is expert in many topics, and his research focuses now on exploring exotic phases of matter out of equilibrium and universal and rigorous results in non-equilibrium quantum dynamics. So please, Zongping, the floor is yours.
Thank you very much. Thanks for your kind introduction, Federico. So hello, everyone. I'm Zongping. As Federico said, I'm from the Department of Applied Physics, U Tokyo. And it's my great pleasure to be here to talk about my recent works with my own student. And I will focus primarily on this published work, but will also mention briefly about this more recent preprint. And the main topic is quantum entanglement. This should be something you're very familiar with. And in the most general definition, it refers to some multipartite mixed states that cannot be written as a classical mixture of product states. But in general, it's very difficult to tell whether a general mixed state, multipartite state, is entangled or not. But things become much easier if we talk about bipartite entanglement in pure states. And in this case, the entanglement is fully characterized by the so-called entanglement spectrum, which is the eigenvalues of the reduced density matrix. And in today's talk, we will focus on this simplest case, a bipartite entanglement in pure states. And we would like to understand how this entanglement structure is constrained by various symmetries. And in part one, I will talk about anomalous symmetry, which I will explain later, and random states. So what is the motivation of considering random states? And one good motivation is the so-called black hole information paradox. So roughly it says that suppose a qubit is falling into a black hole, then the quantum information will get lost. But on the other hand, the quantum mechanics, the underlying physical rule should be reversible, the time evolution is unitary, then how to resolve this paradox? And from the modern point of view, we know that the information does not really get lost, but rather it is scrambled or delocalized. And in principle, if we can collect all the Hawking radiations in this case, we can recover the quantum information. Then how to characterize this delocalization? Then we can use the entanglement between the Hawking radiation and the remaining black hole. And according to this seminal work by Don Page, he modeled the black hole's quantum state as hard random state, and he computed the average subsystem entanglement entropy, and he found that the entropy almost saturates the maximum value. So this is a famous Page curve. And another good motivation arises from quantum statistical mechanics. So how can we derive statistical mechanics from quantum mechanics? And one possible way is to use the concept of canonical typicality. Say, suppose that the entire state of the system of interest in the environment is pure, and it is a typical state according to the so-called major concentration. The state of the environment, not environment, the state of the system is well approximated by that predicted by statistical mechanics. Okay, and another keyword is symmetry. I think it's rather trivial to explain the motivation of symmetry, as this is arguably the most important concept in physics. And here I would like to say a few words more like from the mathematical point of view. So in random matrix theory, which is widely used to describe physics related to randomness, there are three fundamental symmetry class, or the random matrix ensembles. And in the case of random reduced density matrix, so they are the so-called Laguerre ensembles. So the reduced density matrix is given by this W and this W is not just non-Hermitian, but it's not even necessarily a square matrix. And its entries are some IID random numbers that can be real or complex or even quaternion. And physically, they correspond to the Euro-time reversal symmetry, squares to identity, and no symmetry. And this is actually the underlying random matrix ensemble for the original page curve. And if it's quaternion, then that corresponds to the so-called anomalous time reversal symmetry, squares to minus identity. And maybe you are more familiar with the Hermitian or the Hamiltonian counterpart, say. So we have a random matrix that is Hermitian, it is square matrix. And then they are described by the so-called Gaussian ensembles. And depending on whether the entries is real, complex, quaternion, that's GOE, GUE, and GSE. And they can be distinguished from each other by, for example, looking at the level spacing statistics. And as I mentioned that the random matrix ensemble underlying the original page curve, which does not require any symmetry, is the LUE, Laguerre unitary ensemble. The natural question is, so whether the remaining two fundamental symmetry class, LOE and LSE, correspond to some kind of page curve. And for LOE, this is indeed the case. Say, we can impose the normal time reversal symmetry to the entire random state. And on some basis, it can be represented as a random real vector. And if we look at the reduced density matrix, then we will indeed obtain the Laguerre orthogonal ensemble. And naively, you may think that we can do the similar thing using this anomalous time reversal symmetry squares to minus identity. Say we impose this anomalous time reversal symmetry to the entire random pure state. And if we look at the reduced density matrix, then it gives the Laguerre symplectic ensemble. But unfortunately, this is not the case because due to the Kramers theorem, there is no anomalous, there is no time reversal symmetric state with respect to this anomalous time reversal symmetry squaring to minus identity. Because if we apply this time reversal symmetry operator to an state, you will end up with an orthogonal state. So that means it cannot have any eigenstate. Then how to construct the RSE in a way similar to page curve? And the solution turns out to make use of the fractionalization of symmetry. And in this case, for each subsystem, A and B, indeed, the time reversal symmetry is anomalous. Say it squares to minus identity acting on the subsystem. But when we combine these two subsystem symmetries together, then the global time reversal symmetry squares to plus identity, because -1 times -1 equals plus.
Sorry, Zongping, can I ask you a question?
Please.
So when you apply this the Kramer theorem, and you're saying that the average value of the time reversal symmetric operator is equal to 0. So
yes,
the psi that you are looking at is going to be like the universe, the wave function of the universe. Is that what your point is?
Right. It can be an arbitrary pure state.
So
for an arbitrary pure state, we have this relation.
yeah, but in the pictures of page, that would be that you are assuming there is one state which is representing the ground state of your whatever, I mean, universe or whatever.
Oh, right, exactly. That's a random, pure state. Yes.
Okay.
And yes, and if we just like this L or E and we want to import the time reversal symmetry on it, then we will find that it's impossible. Yeah.
But I mean, what if you have some sort of a degeneracy, right? You assume degeneracy, like
right. Yes, exactly. So if we look at the reduced density matrix and it respects this anomalous time reversal symmetry, then indeed we would have the Krom's degeneracy. And that's true. Yeah.
Okay.
So indeed, if we look at the entanglement spectrum, there is degeneracy, but we cannot import this symmetry to the entire pure state. And okay. how to I will talk about how to resolve this.
Okay.
Tension. Yeah. No problem. Yeah. And indeed, so for subsystem, yes, so it's anomalous, and we have degeneracy in the entanglement spectrum. And when we combine these subsystem time reversal symmetries together, then the global time reversal symmetry just squares to identity. Then that's the normal time reversal symmetry. And we can import this normal symmetry to the entire pure state. It's possible. And actually, the same thing happens in the Haldane phase, which is a canonical example of SPT symmetry protected topological phase in 1D. So the Haldane phase is a spin chain, a spin 1 spin chain. Because it's spin 1, so the time reversal symmetry should be this normal one, it squares to 1 because of the integer spin. But if we look at the H, then we will find some effective spin 1/2. And that's why this Haldane phase is novel, it's SPT phase. And we found that for this H states, the time reversal symmetry is anomalous because spin 1/2, it squares to minus identity. But still, if we combine this anomalous time reversal symmetry together, then globally it's still it's spin 1, so it's squared to identity. So exactly the same thing happens in this Haldane phase. And this is more like an idea, and now I will show you that this idea can be made precise. So it is sufficient to consider the minimal example. Say we just consider 2 qubits. And suppose that the entire time reversal symmetry, it's a normal one. So it is represented as a Euro complex conjugate. Then that means that the coefficients are all real numbers. So this x1 to x4 are some real numbers. And then we can rearrange these coefficients into this W matrix, such that WW dagger gives the reduced density matrix. And now we import this upsilon, which is 2-qubit gate. Then we will end up with another 2-qubit state. Now the coefficients are some complex. And the corresponding W matrix turns out to be a quaternion, or more precisely, a spin representation of quaternion. And moreover, if these real numbers are some IID, random real numbers, then this will be a random quaternion. So this is the minimal example of ARC. And in fact, this choice of upsilon is of course not random, and it has already appeared in the literature. So it is a building block of the so-called Haldane, I would like to call it Haldane quantum circuit. This is in the sense that if we apply this bilayer quantum circuit to a time reversal symmetric product state, we will end up with the Haldane state. And this building block, this upsilon has a property that if we take the complex conjugate, then it is equal to applying some single qubit gate I sigma y. So in other words, the complex conjugate, the normal time reversal symmetry is fractionalized into some anomalous symmetries on each subsystem. And now we can generalize this idea of symmetry fractionalization to a more general symmetry group. And this is closely related to general SPD physics in 1D. So suppose, so this is just SPD spin chain, and the physical, on each site, the physical symmetry is represented by this italic D. This is a symmetry representation. But because this is an SPD phase, if you look at the boundary, then we will find that this normal symmetry representation is fractionalized into the so-called projective representation. So they differ from a normal presentation by a U1 phase. And this is just -1 in the case of time reversal symmetry. And this generally, this U1 phase is so-called cocycle. It satisfies this algebraic equation. And we can associate so-called cohomology class to each cocycle. So it's like equivalence class modules so-called coboundary. And it is well known that this is a topological invariant for SPD, and actually it gives the complete classification of SPD phases in 1D. And at least for unitary symmetries, there is an analog of the upsilon. Say we have a SPT quantum circuit in the sense that if we apply this circuit to a symmetric product state, we will end up with an SPD state. And the building block is this omega, and it has the property that if we input the physical normal representation, then we will end up with a fractionalized projective representation on the other side. So in other words, it fractionalizes the normal symmetry into some projective symmetries. So now the question is that can we incorporate this general idea of symmetry fractionalization into random matrix ensembles? And can we build, in this way, can we build new ensembles beyond LOE, LUE, and LC? And to answer this question, so please let me clarify the general setup. So we consider quantum many-body spin system, and it's living on a lattice, which can be an arbitrary dimension, and it has large n sites. And each site is so-called G0 spin, which means that the local Hilbert space is spanned by some bases labeled by group elements. And the on-site unitary symmetry representation is assumed to be regular, which means the action of G on state H gives another state labeled by group element GH. And we may or may not import time reversal symmetry, which induces involutory automorphism of these group elements. And yes, we would like to know the random matrix ensemble related to symmetric random states. So similar to the page curve. And a global state, which is bipartite, is symmetric, means that it is invariant under each symmetry actions. And it may be just the unitary part, G0, or maybe we further have this time reversal symmetry. And technically, it is described by the semi-direct product rather than just a product, because it may induce some non-trivial automorphism. And to randomly sample a symmetric state, so we can perform the sampling within the symmetric subspace of the entire many-body Hilbert space. And the projector onto the subspace is given by the symmetry operators like this. And if we further import the time reversal symmetry, it's not like a further projection onto subspace, but because this is anti-unitary operator, it's more like to enforce some coefficients in this wave function to be real. And yes, so our target is the reduced density matrix, and we want to know so what kind of random matrix ensembles is this, provided the entire symmetric state is hard random. And to simplify this setup a little bit, so first we can reconfigure the lattice. So we can always make it into a 1D lattice because the state is completely random, and typically the entanglement is of volume law. So it does not really make sense to distinguish a site inside the bulk of a subsystem from that near the boundary of subsystem. So we can freely reconfigure these sites. But this is more like a Gedanken experiment. But if we really want to physically reconfigure this lattice, it is possible. So it has been recently realized in this Rydberg atom array experiment. And the second technique is to perform the so-called symmetry concentration. So remember that we are only interested in the entanglement, bipartite entanglement property. And this property is not changed by local unitary transformations. And remember that we assume the on-site symmetry action is regular. So according to the representation theory, the character theory, we know that there always exists a local unitary transformation such that the symmetry operator is concentrated onto a single site. And after this concentration, the symmetry state condition becomes very simple. So the symmetry operator is concentrated. We only have this DG tensor 2, so it means it only acts on 2 sites. And we can explicitly write down a randomly sampled state within this symmetric subspace. So we can write down this randomly sampled state in terms of some IID coefficients C. It is labeled by some remaining degrees of freedom labeled by large R. This corresponds to the remaining degrees of freedoms in subsystem A, and labeled by large R correspond to remaining degrees of freedom in subsystem B. And on top of an element in the group. And this is determined by the element on this site R and small r, GR and GR via this relation, GR inverse GR. And this relation comes from this symmetry condition. So it comes from this DG tensor 2. And if we further enforce the time reversal symmetry, then essentially this enforces these IID complex coefficients to be real. But in general, it induces an automorphism. So we have a theta here, but if it's trivial, then indeed this is just means these coefficients are real. But so far, it's just the normal symmetry, and we can further perform symmetry fractionalization. And remember that for the time reversal symmetry, we have this upsilon gate. And for the unitary symmetry, we have this omega gate. And it turns out that we only have to combine these 2 gates. Then we can fractionalize a general symmetry group G0 semi-cross time reversal symmetry Z2. And this is because a cocycle of this group can always be decoupled into the unitary and anti-unitary part. This is a highly non-trivial result, but indeed there is a rigorous proof in the appendix in this paper. And thanks to this property, so we can write down the random matrix elements for this reduced density matrix. So it suffices to write down the elements for this W because the rho is just WW dagger. And compared to the case without symmetry fractionalization, which are some IID coefficient C, now we have this additionally, this U1 phase, so which is nothing but this cocycle omega. And if we further import time resource symmetry, then essentially these coefficients becomes real. And if the time resource symmetry is fractionalized, then essentially there are some quaternions. So maybe this general result appears a bit abstract, so please let me explain in a more concrete example. And this is actually a minimal example where the unitary part is Z2, the smallest non-trivial group. And first, please let me focus on the case without symmetry fractionalization. So we just import this Z2 symmetry. And we will find that because of this GR inverse GR, then each 2x2 block in this W matrix takes the form like this. Say the diagonal entries are the same, and the off-diagonal entries are also the same. So they are independent random numbers. And we can diagonalize this 2x2 block to get some diagonal matrix like this. And if this C coefficients are IID, then we know that this plus and this minus new random variables are also IID. So it's easy to check the independence of these random variables. So we know that the resulting random matrix ensemble of the reduced density matrix is a direct sum of two independent LUE if we do not impose time reversal symmetry. And if we impose time reversal symmetry, and in this case, the automorphism is always trivial, then indeed these coefficients become real. So we get a direct sum of two independent Laguerre orthogonal ensembles. This is quite intuitive because we have a symmetry Z2, and it just gives rise to a direct sum of two independent random matrix ensembles. And now we move on to the case with symmetry fractionalization. And in fact, this unitary part itself cannot be fractionalized because the second cohomology group of Z2 is always trivial. But the fractionalization becomes possible if it is combined with time reversal symmetry. So essentially, these coefficients are some real numbers because we have to impose time reversal symmetry. And remember that the effect of symmetry fractionalization is some U1 phase on these IID coefficients. And in this case, it's just a -1 phase on one of the off-diagonal elements. So each 2x2 block just looks like this. And we can diagonalize it to be like this. And we found that because the C are real and IID, so we get a pair of IID complex numbers. So upon symmetry fractionalization, the reduced density matrix ensemble is just a direct product of LUE, but they are not independent, but rather complex conjugate of each other. So this means that the entanglement spectrum is twofold degenerate. And while this is far from trivial, so we can show that even if we fractionalize the time reversal symmetry, again, we will end up with this a complex conjugate LUE ensemble. And also we can fractionalize the time reversal symmetry alone without fractionalize the unitary part. And in that case, as you can expect, it's just a direct product of two independent Laguerre synclitic ensembles. And this is just a simple example, but it's already very rich. So we see there are many different possibilities like direct sum or LOE, LC, and LUE. And it turns out that even if the symmetry group is very general, we still have this decomposition into elementary random matrix ensembles. So please let me give a rigorous statement of this general result. So first, let's focus on case without time reversal symmetry, just some unitary symmetries. So the decomposition is just into some Laguerre unitary ensembles. And it is labeled by, so each independent LUE block is labeled by some irreducible representations of the group. And it can be projective if the symmetry is fractionalized. And also there can be some degeneracies depending on the dimension of the array. And if there is time reversal symmetry, then things become more complicated. So in general, the reduced density matrix ensemble can be decomposed into, so it will consist of all of the three elementary building blocks, say LUE, LOE, and RCE. And again, the independent blocks are labeled by the array of this unitary part G0. And it depends on whether the Schur-Frobenius indicator, so here is the formula for this indicator, it can only take values 0 or +1 or -1. So depending on this indicator, so we know whether this alpha block corresponds to LUE or correspond to LOE if it's plus. So this is 0, it corresponds to LUE. If it's plus, it's LOE. If it's minus, it's RCE. And if we further fractionalize the time reversal symmetry, so which means this omega TT is -1, then what happens is we interchange the LOE and RCE blocks. And this general result can be considered as the entanglement or Laguerre counterpart of the famous result by Dyson, so who showed that for a random symmetric Hamiltonian, which is a Hermitian, it can always be decomposed into a direct sum of GUE, GOE, and GSE blocks. So here we just do the entanglement counterpart. And as a final remark of part 1, I would like to emphasize that the degeneracy in the entanglement spectrum does not necessarily require the symmetry fractionalization. And here is a minimal example. Say this, if the symmetry group is C3V, so this is the minimal non-abelian group. And because it has a dimension 2 array, so we have 2 for degeneracy for this block. And if we further import time reversal symmetry, then all these LUE blocks are turned into LOE blocks. And in fact, even a non-abelian group is not necessary for creating degeneracy in the entanglement spectrum. And here is a minimal example of abelian group, so which is Z3 cross Z2. This is time reversal symmetry. And the corresponding reduced density matrix random matrix ensemble is LOE, direct sum of LOE, and a pair of complex conjugate LUE. So there is 2-fold degeneracy. And this is to be compared to the semi-product because there is a non-trivial automorphism on this 3 group. And in this case, the random matrix ensemble is just 3 independent LOE blocks. And finally, we can also have RSE degeneracy, and this happens without fractionalizing the time reversal symmetry. And this happens for the so-called quaternion group. It has a dimension 2 array whose Schur-Frobenius indicator is -1. So it gives rise to an RSE block. Okay, so as a short summary of part 1, so the main point is that if you want to construct a Laguerre symplectic ensemble in a way similar to page curve, then it's necessary to incorporate symmetry fractionalization. And in this case, that's the fractionalization of time reversal symmetry. And this is exactly what happens at the edges of the Haldane phase. And by generalizing the idea of symmetry fractionalization to arbitrary symmetry group, we found that the random matrix ensemble of the reduced density matrix can always be decomposed into the threefold way, say the LUE, LOE, and LSE. So this can be regarded as the Laguerre ensemble counterpart of Dyson's classical result for Gaussian ensembles. So I think I still have some time, so please let me move on to part 2. And in this part, we will talk about a much more non-conventional symmetry, which is D+1 form RIP-G symmetry. And I will explain it later. And before that, please let me give some general introduction to so-called generalized symmetries. And in recent years, it is widely recognized that the class of symmetries can be much broader. And they are generally called generalized symmetries. And one big class is called a higher form symmetry. So the Euro symmetry, as we talked about in part 1, that's the so-called zero form symmetry. So it acts on the entire system. But a higher form symmetry just acts on a lower dimensional submanifold. And here is a simple example of one form symmetry in 2D. So the entire system is 2D, but the symmetry operator just acts on a 1D submanifold. So it's indicated by this red curve. So the codimension is 1, this is one form. And in general, if the codimension is P, then that's called a P-form symmetry. And there is actually an important feature of higher form symmetry is it should be topological, which means if we continuously deform the submanifold of where the symmetry acts on, then its action should be the same. And in particular, if we can continuously shrink a small loop, so that's why this loop disappears on the right-hand side. Okay, but this is just a way, so how the range of the action of the symmetry. And there is another kind of generalization concerning the algebraic structure of the symmetry. So the Euro symmetry is described by a group, but in fact, there is a much broader class, and they are usually called non-invertible symmetry or categorical symmetry. So they are described by a more complicated algebraic structure called fusion algebra. Say the action of symmetry beta followed by alpha turns out to be some linear combinations of some other operators gamma, and the coefficients are some non-negative integers. And indeed, if these coefficients, sometimes called fusion coefficients, if it is 1 for a specific gamma, but otherwise 0, then we return to the case of a group. So in this case, in this sense, this is indeed a generalization of the Euro group symmetry. And there is actually a very nice example of this fusion algebra structure related to group. That's nothing but the group representation, and supports this alpha and beta are some irrape of the group. Then indeed we can decompose it into some other irrapes, and the coefficients can be determined using the character theory of group representations. And in fact, if we regard this fusion algebra of representations as a symmetric tensor category, then we can completely recover the group itself, and this is called the Tanaka-Klein duality. And in fact, there are the fusion algebra itself is a much broader class, and there are fusion algebras that are not group representations. And the minimal example is the Fibonacci fusion algebra, where there is just a single non-trivial element on top of this trivial one. And its self product just gives 1 plus this tau. And you can check that the effective dimension of this object is the golden ratio, so it's not an integer. So it's not a group representation. Okay, now we can explain, so what is D-1 form RIP-G symmetry? And because it's D-1 form, the codimension is D-1, so the symmetry acts on one submanifold. So the symmetry operator can be described by a matrix product operator, which is a one-dimensional object. And also, the fusion algebra is nothing but that of the representation ring of G. So it turns out that the NPO operator can be simply built from the representation matrix of the group G. So this D alpha.
Sorry,
please.
What's the total dimension we are talking about here? Because you said that we go from dimension 2, and the group applies only to a one dimension. Is that correct?
Okay, so you mean the dimension of the entire system?
Yeah, the dimension.
So
yeah,
because we are this D. Okay, right.
Okay.
This D can be arbitrary actually.
Okay.
And right, can be arbitrary. So, and because it's D-1 form, and so P is D-1, and D-1 is just 1D. So that means the symmetry operator always acts on some 1D manifold. So it's a one-dimensional object. Right.
Okay.
This just means one dimension. Yeah.
Okay. In the matrix picture, matrix product operator picture, the D is encoded in the internal dimension of the, let's say, the operator.
No. So the D is encoded in the entire system, the lattice where the system lives on.
Okay.
So in this case, it's 2D, right? But it can be general.
Okay.
But even the NPO symmetry, so because it's matrix product operator, it's 1D, right? It's always act on some 1D submanifold.
Okay.
Like this radial loop, right?
Okay.
And the entire system, in this case, it's 2D. Yeah, but it can be general, more general. Yeah.
Okay.
Okay, thanks. And because this is RIP-G symmetry, so the building block of this NPO symmetry is nothing but the representation matrix of some rape alpha or beta, and these coefficients can be computed using the character theory. And now we would like to know how would the entanglement, bipartite entanglement, look like if manifold state respects this generalized symmetry. So yes, the manifold the system live on can be an arbitrary D-dimensional manifold. So in this figure, we just give an example of a 2D manifold. And we just discretize this manifold into a graph. And so this is kind of a lattice, and we make a bipartition. And we would like to know the entanglement spectrum. And there's a small difference from the setup in part 1. And now we put the G spins onto the edges rather than onto the vertex due to some technical reasons. And the manifold state is symmetric with respect to this D-1 form RIP-G symmetry. If it is symmetric or the action of the NPO built on some contractible loops is trivial. And usually the trivial action is just equals to the state itself. But now because this is invertible, so there's some technical difference. It's generally an integer D alpha larger than 1. And this is just the dimension of the array of alpha. And if G is abelian, then indeed all the array is one-dimensional, then the D alpha is 1. It's just the Euro invariance under the symmetry operator. And here, this bracket air equals to point just means, so this is a trivial element in the fundamental group. This means, just means this loop is contractible. It can be shrinked into a point. And in contrast, the dashed loop here, this is a non-trivial loop due to the non-trivial topology of the underlying manifold. And the action of this loop may be non-trivial, but the action of the contractible loop is always trivial. And although this condition may seem a bit difficult, but if the state is just a product state of some local G labels, then it turns out that this symmetry condition is nothing but that any small Wilson, so small just means contractible, like this solid loop. Any small Wilson loop is trivial. Say this loop will collect some group element labels, Gj, along this loop. And also you can see this Sj here. This is due to some technical reasons that the orientation of the graph and the loop may be opposite. Then we have this -1, otherwise there's 1. So we have an ordered product of these elements G, and it should be the trivial element. So in other words, this gives a flat connection on this lattice. And using this property, we can figure out the general block structure of a state that is symmetric with respect to the D-1 form RIP-G symmetry. And it is sufficient to consider the W matrix because, as I mentioned in part 1, the reduced density matrix is just WW. And we found that this W matrix can be factorized into a geometric part and topological part. And we found that this geometric part is highly fragmented. So there are many blocks or sectors. And the number is, I would call it area law fragmentation. It is proportional to the Hilbert space dimension of the boundary. So we have this V partial is just the boundary here. And also, so each sector is itself very large. It has volume law large degrees of freedom because we have this volume or the number of vertices of, subsystem X and subsystem Y. And because the RIP-G symmetry is actually non-abelian, so it's rather reasonable to see that there's no degeneracy in this W matrix. And indeed, this depends on the size of the subsystem and the boundaries, so this is geometric. And the topological part does not really depend on the size. As you can see, you can obtain all these numbers using some topological computations. This is just some fundamental group point and some homomorphisms. So it does not really depend on the size, but only depend on the topology. So I will not go into the detail, but I think this can convince you that these are just some topological numbers. And this is to be compared to the zero form group symmetry in part 1. And remember that we can do reconfiguration. That means it does not really depend on topology of the underlying manifold. And also, we only have order 1 fragmentations. So they are labeled by the numbers of irreps of the group. And also, we can have some degeneracy if the symmetric group is non-abelian. So this is some comparison between the conventional group symmetry, zero form symmetry, and this D-1 form RIP-G symmetry. And this is just an example showing that we can indeed compute the, I only show some topological degrees freedom here because the geometric part is a bit boring, and it's the same for these two cases. And because the topology of the entire manifold are different and the bipartition is, of course, different, then we have different block structures in this topological part. And there is actually a very nice situation where we can eliminate this geometric degrees of freedom. And that is, we can further impose gauge invariance to the global many-body state. And actually, this makes the setup a topological gauge theory. And in this case, the geometric degrees of freedom are killed. Say it is fixed to be some identity tensor. So I write 1 here, but actually this means a matrix with all entries being 1. So this matrix is actually of rank 1. So after normalization, we can check that this is an area law entangled state. And because we have this identity here, the area law microscopic fragmentation now it becomes a microscopic degeneracy. And also the gauge invariance constrains the topological part. And so it may induce some degeneracy here. I do not know how to call it in higher dimension, but at least in 2D, this is nothing but the annual dimension. And I will not go into detail, but indeed we can figure out all these details using some algebraic topology techniques. And in particular, in 2D, the topological gauge theory becomes nothing but the Kitaev quantum double. And if the group is state 2, then that's the famous toric code. And in this case, we can compute the entanglement entropy of the subsystem, and we can identify the negative correction to this area law. And this correction is nothing but the topological entanglement entropy. And for this trivial cut, which means the subsystem X is just a disk, or topologically a disk, then we will reproduce the well-known result. So it's just log the number of group elements. But if we have a non-trivial cut, so the subsystem is a tube, so the topology is completely different from this disk, then we have a different expression for this topological entanglement entropy. So now we have this 2 here because the tube has 2 boundaries. Unlike this disk has only 1 connected boundary, so it has 2 disconnected boundaries. And also it now depends on the ground state, but this result does not depend on the ground. So remember that the ground state of Kitaev quantum double is there's degeneracy on a topological non-trivial manifold like a torus. And if we make a trivial cut, this does not depend on which ground state you choose. But for this cut, it does depend on that. So we have different kind of terms. And we can even figure out the expression of the remaining degrees of freedom. So you can compute this X and Y. And it turns out to be given by this so-called Ferlinder formula. And it's basically, so it is in terms of so-called S matrix. And it measures how many different ways that we can fill, these annuals can fill up. And this is kind of a manifestation of so-called Li-Hao-Den correspondence, which claim that the boundary physics of a Hamiltonian, so put on an open boundary, is very similar to the entanglement spectrum. Oh, sorry. Yes. Okay, so as a short summary, so if we import the higher form symmetry into a manifold state, then we will get a macroscopic fragmentation. So there will be many blocks. And also there will be generally some topology dependent degrees of freedom. And if we further import gauge invariance, we will obtain some topological gauge theory, and then we can reproduce a well-known result about the topological entanglement entropy, and we can even generalize the result for the non-trivial bipartition. And we can even explicitly demonstrate the Li-Hao-Den correspondence concerning the 4 entanglement spectrum. I also have a few slides regarding the future studies, but I think I'm running out of time, so I'd like to stop here. So thanks for your attention.
Okay, thanks, Zongping.
Thanks.
Are there any questions from the audience?
Just everybody, a curiosity. So when you mentioned the symmetry, or sort of a categorical symmetries that
right.
That you use, for example, for the case of the toric code, would that be in the case of the just to?
Okay, so actually, there is a one-form symmetry, and in that sense, it's a generalized symmetry, but it's not categorical. It's just a RIP Z2, so the toric, and the RIP Z2 is exactly Z2, and this for any abelian group, the representation is just the group itself, and this is called the Pointelier duality. Yeah, so only for some non-abelian groups, then we get indeed a categorical symmetry that is not a group.
Okay, so that doesn't have anything to do with the anionic structure of the excitation in this type of in the toric code model.
Right. In the toric code, yes, it's abelian. So and as you can see, that actually this annual dimension is just one.
Okay.
So, but otherwise, if there's a quantum double for non-abelian group, then we can have a larger than one annual dimension. Yes.
Okay. No, because I remember that if you look at the type of excitations that the toric code has beyond the ground state excitation, one can show that the type of excitations are anionic excitations, and then you can also come up. You can also come up with a series of fusion rules between the type of excitations. And I was wondering whether there is a sort of a connection between those fusion rules.
Right.
So the symmetries.
Yes, I see your point. And actually, so if you talk about in that case, it's not this RIP G part, but it's a bit tricky. So actually, that fusion rule corresponds to the so-called dream field double of this group symmetry, and it can be non-trivial. And but if you only see this group, then it's just a representation. And as you can see here, we have this bracket phi and this alpha phi. So I just skip the details. So actually, this bracket G is just the conjugacy class of the group element, and also you have a rape of this so-called stabilizer group, and a pair of this rape label alpha and the conjugacy class labels an annual type, and that is a so-called dream field double. So it's a more complicated structure than just the group representation. And I think you are talking about the fusion rule with respect to that dream field double, and that's indeed non-trivial. Yeah.
Okay, thanks.
Yeah, thanks.
Okay, any other questions? Well, if not, we can thank Zongping again for the nice talk.
Thank you very much.
Great. So I guess, yeah.
Yes.
Then.
So actually, it's bye. See you.